Okay, hi everyone. I'm Dingwen Tao from Indiana University. So I'm an associate professor in the School of Computing and Informatics. So today I want to touch a little bit on the lossy compression with the HDF5. I have been working on the lossy compression. I see there like a lot of discussion about compression. I try to link the things with what we just discussed, and I think that's a pretty interesting discussion. I appreciate that. So actually, you can treat me as a compression developer, algorithm designer, and we implement the different types of a compression algorithm and software. So I don't want to spend too much time on the motivation, right? That's a general motivation. I think people here are expert on the I/O and the storage, but in general, I think the motivation for us to develop the compression algorithm, especially the algorithm that can provide the higher and higher ratio, because as we just discussed, we have some scenarios needs to have a very high compression ratio, but sometimes we need to have a high throughput for the compression algorithm, right? But in general, the reason why we want to have like some compression algorithm is like the storage and I/O issue is becoming more and more severe. If you look at the recent supercomputers, especially the computing power versus like storage capacity and the I/O bandwidth. I don't want to spend much time on the data, but that's obviously a problem for us. And from the application perspective, we are collaborating with a lot of like domain scientists, application developer. They are running their simulation on the supercomputers, so they are facing a lot of like storage challenge because the simulation can generate a lot of like data. For example, we are collaborating with the cosmology simulation team from like Department of Energy, so they can easily generate tons of like petabytes of the data just to simulate the our universe and understanding the future of our universe, right? And also like climate data. People know that the climate simulation eats a lot of like resources, right? No matter the computation resources or storage resources. So it's very hard to handle this data efficiently. And also like some instrument, right? So DOE National Lab are building a very, I think yesterday keynote, right? So we have like a lot of like instrument generating the data. So it's very hard to handle this data, especially between the data generation source and the data processing facility, right? So that's all the reason why we need to have data reduced by tens to 100 times. So our solution to handle this like big data issue, especially big scientific data issue, is to develop an efficient, effective lossy compression, because our principle is compared to the lossless compression. So I'm also doing some research in lossless compression, but our argument here is like a lossy compression, sorry, can relatively provide a higher compression ratio. For example, there is some study talking about lossless compression on the scientific data, floating point data, just to provide a compression ratio of 2, but compared to lossless compression, lossy compression can provide more than 10 times of the compression ratio. But the challenge here is like, and also like people have a lot of like image compression, which is a lossy compression, right, developed in the past decades. But what's the uniqueness of the scientific data lossy compression, right? So I think the main difference is like for the scientific analysis or discoveries, people need to have like a very strict control of the error introduced in the data, right? It's not like an image or like a video, right? As long as you can recognize this image or videos, then that's fine. But for scientific data, we don't really know what type of the error you introduced. So we need to have a very diverse and strict error controlling techniques. For example, we need to control for each data point by maybe some bound, right? And also you want to control some like a L2 norm or IMSE based error, right? And sometimes you need to control the compression ratio or the bit rate after the compression, right? To provide the stable throughput. And also we want to, not only for the data itself, but also for the post-analysis, right? For example, we are collaborating with cosmology team. They are doing some FFT-based spectrum analysis. So they really require the data analysis on the reconstructed data to within some like fidelity. So we also need to satisfy their like requirements. So from like maybe 6 or 7 years ago, we as a team collaborate with Argonne National Lab. So we have developed a lossy compression framework called the SZ lossy compression. So this lossy compression, we know there are a bunch of like lossy compression compressors in the community. So our technique actually is a prediction-based technique, and we can provide a very strict and accurate control of global upper bound of the compression error. And we also have implemented on the different computer architectures like CPUs, GPUs, and we also have some prototype of the FPGAs in, just for like for example, we can put the compression near the computing facility, right? And we have integrated into different I/O libraries. So, for example, HDF5 audios. But I think for the reason I attended this user group meeting, because recently we heavily use HDF5 as our middleware layer to incorporate our compression algorithms and evaluate the performance and the I/O performance things. I will talk about that slightly later. And this is like some technical part of the compression pipeline. As I mentioned, it's a prediction-based approach, so we need to have like a different prediction approach, predictors, and we are doing the quantization because we are the lossy compression, right, rather than lossless, and we are doing some encoding techniques. So I think we treat this compression framework as a very flexible, modularized compression framework, rather than like a specific compression algorithm like a gzip or other LZ compression, lossless compression, right? They are pretty fixed, and our techniques actually are pretty flexible, so we can change the different parts. For example, decorrelation, we have the different prediction technique, Lorenzo predictor or other like predictors, depends on your requirement of the ratio of the throughput, right? And for the encoding, different data have different distribution, for example, and we should use a different encoding techniques. So actually, our framework is a very pretty good framework, and we have been supported by DOE, NSF, and some like research companies for their interest in research. And I think for the scenarios, I think pretty interesting. Like we can help with reduce the storage footprint. We can accelerate I/O communication. We can sometimes accelerate visualization because you don't really need to move the data back and forth between the storage system and the memory, right? So we just keep the compressed data in the memory, and we have different scenarios. Sometimes recently we are trying to think about like some AI use case, like reducing the training, reducing like as a keynote speaker this morning say that, right? So training spend consume a lot of like resources. So we want to help with the data issue. And here is like so as I mentioned, so compression can survive independently without other tool ecosystem, but actually we are thinking we really like the HDF5 ecosystem, right? So it provides a user very friendly environment to transparently using compression, right? And we also realize that though some application users, they don't really know how to use compression, right? Especially for lossy compression, some error bound or whatever. So we want to integrate our compression algorithms into the HDF5 ecosystem. So as you see here, so our filter has been developed, and you can easily call our compression algorithms in the HDF5 using HDF5 compression filters. And we have a different, we have different error control mode, and you can pass this control mode parameters to the filter, right? And as I showing here, so we actually have developed a different compression, a version of the SC lossy compression, and our ultimate goal is to provide a very modularized, composable compression framework, which can provide the greater flexibility in configuring compression pipelines, right? So far, we're still developing that, but I think eventually you can pass, for example, different predictors, different quantization, different encoding techniques as a parameter to the filter, and the filter can automatically construct the compression algorithm and automatically call that in the when you dealing with the data. So I also want to say something here, like we have some bunch of like undergoing projects. Mostly we are focusing on the compression algorithm design, but almost every project, when we mention how we want to use it to adopt our compression algorithms, we want to say something with collaborating with the HDF5 team. For example, I'm closely collaborating with Suren on the using evaluating compression algorithms through the HDF5 parallel IO, and we recently also got an NSF big project about 3.5 million to develop our next phase of the compression algorithms. So here is like the project overall goals, and I think I don't want to talk too much details, but here I think our vision is like we want to use in the future to customize their compression algorithms using our techniques, right, through a very easy programming interface, and it's like a PyTorch generating like neural networks, right? So we want to user can easily generate their customized compressor through the Python API, Python interface, and they can, through our like a backend provided compression modules, as I mentioned, different encoding techniques, different prediction techniques, and they can easily compose a compression algorithm. After they generate the compression libraries, and they can go through the HDF5 to call that in their like applications. And our tools can also provide the people like some quality assessment and visualization techniques to play some trade-off here. Okay, and besides the lossy compression, actually, I think the previous speaker also talk about some benchmark things. I think benchmarking is very important because I think there was a question discussed. Is compression ratio more important or compression throughput more important, right? So actually, I don't think that's that's an open question. Different scenario definitely require different things. And actually, we are building a benchmark a suite and the tool chains, and we are trying to release the work, but it's still like a paper is under review, and the GitHub repo is private. But I want to show to the community here, like we have like this benchmark repository, and I think HDF5 play a very important role. Sorry for this very small box, but I think here is like we plot HDF5 in this like benchmarking suite. Like we want to, because not all the compressors they have HDF5 filter or whatever, but we can use the Python interface and the data frame to read the data from HDF file, and then query the data on the data frame through the HDF5 file. So we are trying to understand sometimes ratio is more important or throughput is more important, right? So do I use my time already? Yeah, I mean, yeah, yes. Okay, so I think actually I don't have much time to go into the detail about our work. I just have 3 slides. I want to quickly talk about that. My students will also give a talk about the details this afternoon. But I think here is the first work I want to very quickly talk about. That is like a compression with I/O. People may think, okay, it's easy, just compress and then call HDF5 or parallel I/O library and save the data, right? But actually, I want to say something here. Is like it's not. You can use that like this, but actually we have some optimization room here. For example, the work we did in last year supercomputing is that we noticed that compression and I/O actually they are sequential job, right? After compression and then I/O. But we realized that if we can do something better, understanding the compression stuff, we can maybe launch the I/O operation or parallel I/O earlier than you finish the compression, right? And the reason we cannot do that is that we don't know the data size, compressor size before compression, right? Then not like without a compression, okay, this file is 1 megabyte, this file is 10 gigabytes, right? So you can set the offset and you can do the parallel I/O. But with the compression, you don't really know the compression size, compress the data size, right? So in this work, we are trying to predict the compression result, and we are trying to launch the I/O operation even before we finish the compression, right? And there's some work we did for this year, so we are trying to customize, as I mentioned, customize the compression algorithms to specific application. For example, here is that we are doing the AMR simulation, and we are using the AMRX framework, and we are trying to pre-process the data and using compression techniques, and we also need to slightly modify the HDF5 filter to accommodate or modify our compression algorithm here, and we are achieve the I/O performance speed up. And the last slide I want to show here is like not only the HPC application, but for the machine learning application, we realize that I/O is a severe problem. And for a lot of like deep learning training, people are using HDF5 to save the data, to save the image, right? And the random access the data and the different pattern of the parallel I/O. We are here using the HDF5. You see that we test different patterns of the I/O access pattern, right? And we see, okay, the performance is totally different. So that's why we need to think about how to do some optimization for the I/O stuff, even in the deep learning stuff, right? So I don't go into the detail, but after our optimization, we can increase the I/O speed in the deep learning training. So I think that's all for my today's talk. Yeah, thank you.
Thank you. When you talk so fast, I can't really keep along. It's great effort there.
Yeah.
Any questions?
Okay. What is the canonical way to obtain your software? Because I think you showed the HDF5 plugin package for Python. But now, let's see, if I go to the HDF group, HDF5 plugin repo, I don't think I find SC3. And I'm not sure if SC compressor is the latest.
Yeah, I think for now, I think the compression filter all developed by our compression software developers. So I don't think our filter is including in HDF5, but I think the compression filter software package is in SC3 GitHub repository, and we have separate like a filter for the old SC compression. So, but in the web page you can find SZFP, SD, or other compression filters and their IDs. Right. You can know we are there. Yeah.
So with like the Python package, do you update that, or does the package maintainers go grab your source and update that?
I think we need to discuss with them. We want to be included, and I don't think we frequently update that because for the Python things, after it's there, it's just there. But I think we need to initiate this like discussion. Like we want to include our software into spec, right? We need to do some pull requests to let the spec team know, okay, our software has been incorporated with the spec, and after that, if they find any problem, they will notify us. Yeah.
Right. Okay, because I think that's a rhetorical question I have, right? Is where is a canonical place to get the filters? If they mark other lines of benchmark, where do you get them from? So
right.
I don't.
Right. I think it's a good problem. It's a good question. I think we need to do some better like dissemination, maybe interact with the HDF5 and see how we can better like showing our software in the HDF5 maybe.
Thank you so much.
Okay. Thank you.